remarkable is the numbers that we measure experimentally are very similar to what he calculated there. Now this may be a complete coincidence, because he calculates his spin Hall conductivities for the perfect crystal with no impurities or defects. So it's what's called the intrinsic spin Hall conductivity, which uses a mechanism slightly more difficult than what I explained to you earlier. But in our samples, we have polycrystalline samples with defects and impurities and all. And so that in our measurements, the intrinsic contribution would dominate is not clear. So what we need to do is do more experiments as a function of temperature or as a function of microstructure, see how robust these numbers are, how they change when we vary the parameters, to really see if we look at intrinsic or extrinsic effects. Now, what is interesting is now these spin Hall effects, though, they allow us to connect charge currents to spin currents in a fairly straightforward way. And since theoretically it seems that we can calculate them fairly robust, we can use theory as guidance to identify materials where this coupling is really very effective. I mean, right now the conversion is like 1%, that's very low. But if we get materials where the spin Hall angles are 10%, then it becomes really attractive even for applications. But nevertheless, there's some interesting experiments that been done now last year, again in a group in Japan. What they did is they used a ferromagnetic insulator, yttrium iron garnet, and put 2 platinum contacts on top of them. And now they do a very strange experiment. They pass a current through the platinum. Now we know what happens when you pass a current through the platinum. You get a spin current that's perpendicular, and then it hits a ferromagnetic insulator. Well, it's an insulator, so the spin current doesn't go in there, right? But it turns out that nevertheless, if you have a spin current hitting the interface of the insulator, you start exciting magnetization dynamics. You start exciting spin waves of sorts. And these spin waves can travel through the insulator, get to the second platinum contact, and then at the second platinum contact, through spin pumping, they can generate a voltage again in this platinum layer. So it's interesting, you can generate a spin current in an insulator and then have this transmit and create an electric voltage at the end. Now, at this point, this conversion is not very efficient. They put like milliamps in here and measure nanovolts there. I mean, there's many ways how you can do this, but it's interesting because it now